let's think more about the derivative of the delta function. This is number 9. I want to lay out what I'm thinking about, what's behind number 9. Um, we've got the formal definition of delta prime. When it acts on a test function phi, by definition of differentiating a distribution, that's minus delta on the derivative of phi, and therefore it's minus phi prime of 0. That is super, super useful. It is the definition. It's what we almost always manipulate with, but it's a little formal in terms of maybe too formal to understand very intuitively. Uh, in the last few problems, in the last video, we basically justified to ourselves that delta prime can also be thought of the limit as an up-down double rectangular pulse with total width 4 epsilon and magnitude height here 1 over 4 epsilon squared. Really important that the area goes to infinity as epsilon goes to 0. Okay, so it's a limit of functions. Now here they're piecewise constant functions. Now let's compare that to what we had for delta. Delta of phi was phi of 0. That's the formal definition. That is the definition. It's the easiest thing to use. But we also were able to think of delta as the limit of a square rectangular pulse with area 1. So here it's 1 over 2 epsilon, not epsilon squared. But we were also able to think of it as the limit of pretty much any kind of decent kind of pulse, as long as it has area 1 and it's squeezing in to concentrate attention at the origin. And I want to look at the analog of this guy, not in an incredibly rigorous way. We'll save that a little bit. And I also want to think about the relationship of like this definition of the derivative of a distribution, which is very simple but very formal, and this notion of thinking of a distribution as a limit of ordinary functions. Now, it'd be a little awkward, although we'll see in the next problem, number 10, maybe how to think about this. It'd be a little awkward to talk about the derivatives of these guys, because that itself brings us in deltas and things like that. But as long as we make this reasonably smooth, like a Gaussian, this has a perfectly nice derivative. So our conjecture would be, if delta is the limit of these guys as epsilon goes to 0, then maybe delta prime is the limit of the derivative of these guys. Basically, it's asserting that derivatives, when you take derivatives of distributions, that's a continuous operation on the space of distributions so that they commute with limits. And we will prove that. But let's just draw some pictures to get us into that idea. So that's kind of the more sophisticated stuff that's behind this. So we just start out with, let's say, f of x is a Gaussian or some other hump. It really doesn't matter. And then do the standard thing we talked about when we were introducing this with delta. As epsilon goes to 0, we shrink it, but then we scale it to have area 1. Okay, and so that's going to be taller and skinnier, etc. Okay, and then I want to look at the derivatives of those guys. Okay, what is that going to look like? F epsilon prime of x. Let me make clear. It's do the f epsilon, the modification, and then take the derivative. Okay, so again, just sketching it. Derivative of that original hump, it's going to go up and then peak somewhere around here, and then go down to 0 right at that symmetrical maximum, because I chose it to be pretty and symmetrical. It's not absolutely necessary. It's kind of perverse not to when we're trying to simplify things. Okay. And then what's going to happen? So that's like maybe epsilon equals 1, the original, and then epsilon equals a half or a fourth or a tenth or a hundredth. It's going to get, it's going to have that same double hump shape, and already we're seeing the double pulse in the derivative that we were expecting to get, but it's going to get sharper and sharper. And so this is going to go up, still down and down. I didn't leave much space there. Maybe we would have, a more extreme version would be like, choo. Oh, this is terrible, but like that. Okay. So really high and really skinny. Okay, a high and skinny double pulse. That's mainly the point I wanted to get across with number 9, is that when you start with these smooth pulses and you take derivatives, yeah, you take the derivative, you get the up-down double pulse that we've been talking about for the last video or so. Okay, but let's look at the formula just real quick, as much as we can. We don't have an explicit formula for this, but the formula, just based on the chain rule, is you're going to get f prime, the standard double pulse for epsilon equals 1, squeezed with an x over epsilon, and then you're going to have the 1 over epsilon that you had already, but then another one from the chain rule. Aha, that's another explanation why in the in that big F epsilon, the forcing function from the last video, we had the epsilon squared on the bottom. Of course, it wouldn't have worked out correctly if we hadn't had the 1 over epsilon squared. But this is a really simple demonstration that if we believe we can approach delta in this way, and that the derivative of delta should be approached by the derivatives of the F epsilons, which is something we haven't really proved, but isn't super hard to prove later, then we should get an automatically 1 over epsilon squared on the denominator here. Okay. So let me just write that down. And this, again, in the worked out solutions on the solution PDF, I talk about this. What we're really trying to sneak up on is this idea that if you take the derivatives of the F epsilons and you take the limit, we'd like to assert that's the same thing as taking the limits of the F epsilons and taking the derivative, which of course is delta prime. But this is a distribution, and this is a derivative in the distribution sense. And is this true that as you modify a function in a systematic way, and what kinds of way are allowed, and you take the derivatives, do you get the derivative of the limit? Okay. So that is going to be a very general kind of phenomenon. But, and certainly with this, when the limit is just rescaling a function, it really is going to work very generally. Okay, so 10, as I said, we could have started with like the rectangular up-down pulse and take the derivative of that. If you take the, oh, that's not very, if you take the derivative, well, then you're going to get like a delta pulse up and then down and then up. It gets a little complicated if you do it that way, okay? So I'm going to just do it in a little bit of a different way. Okay, so what we're going to do is we're going to just have a formalized up pulse and a down pulse. Okay, and that's going to be at minus epsilon and epsilon, and that's representing integration against this guy and integration against this guy, much as we were saying the midpoint rule evaluating at minus epsilon is a good way to approximate integrating against this rectangle, and the midpoint rule here is integrating against that rectangle. So, and it's also, you can also think of it as the extreme version of what we were just showing, super tall pulse, and so this guy gets idealized as a delta and this guy gets idealized as a delta. And they're not both at the origin, or else they would cancel out. They're very close to the origin, but that separation is really crucial. We're going to end up getting a derivative. Okay, so let's look at this. There's a delta, and we got to have them scaled right, and we're going to take the limit as epsilon goes to 0 of 1 over epsilon, actually let's see, 1 over 2 epsilon. I'm going to do the symmetrical version only of this problem. So up pulse, down pulse, and scaled appropriately. And now I'm just going to act with that on phi. And what we're going to get is just the symmetrized derivative that we saw before. It's really easy. By definition, that's phi of minus epsilon minus phi of epsilon. Notice that it's the one on the left minus the one on the right because it's minus the derivative. But of course, that's what delta prime on phi is supposed to get because of the minus sign from integration by parts. Okay. And so this is a very formalized version of this idea that a delta prime is a up-down double pulse. And you can even make, if we think we understand the delta level of distributions, you can just go ahead and say, those are deltas. I love deltas. And then make them get bigger, shoop, as you go in, and narrower, and you get the derivative. You might wonder, where did the epsilon squared in the denominator go? Well, remember, I'm taking out one factor of the epsilon in the denominator by taking a rectangle pulse and turning it into a delta. There's sort of a 1 over epsilon that we absorbed into there. Okay. So let me make this a bit of a short one. The next one, it has some other ideas that'll take us in a slightly different direction. So I'll stop here.